So, unfortunately, I was joking with Katie earlier, we'll only be covering about a tenth of the dimensions promised during today's presentation. But this will be focused on 2D hydraulic modeling and HEC-RAS. HEC-RAS has come a long way since, I've started working, and it's amazing all the features that it has now. And, it's really become a tool where you can do a lot of your workflow in HEC-RAS itself, rather than working between HEC-RAS, AutoCAD, GIS, etc. So there are a lot of new tools that I think are really exciting and applicable to what we do. This presentation will be pretty high level. It's kind of the intro to the application of 2D modeling and then the basics of how to kind of build a model. So there are certainly a lot more details that we could cover and get into, but for the sake of providing kind of a general presentation on when to use 2D modeling and kind of a crash course on how to get one started, I think we'll stick pretty high level with this. So Sam and I have kind of prepared this presentation, and I think we'll go ahead and kind of dive into it. Sam, I think if you want to go to the next slide, I've got an option here to take control, but I think as a presenter, I think it makes the most sense if I just let you know which slides to flip through, and then we can go from there.
Oh, here we go. All right.
Awesome. So a quick overview of the presentation. We'll kind of discuss quickly the types of hydraulic models, the applications for when to use a 2D model, when it's appropriate, and when it might be more beneficial to go another route. The data requirements for a 2D model, as well as kind of the basics, like I said, of building one. How to kind of view the results of a 2D model. That is one of the biggest differences between a 1D model and a 2D model. We're used to tabular results for 1D models, but the nature of a 2D model and the distributed fashion in which those results are presented do not lend themselves well to kind of a tabular format. So we'll go into that. Sam will also discuss kind of how to assess the reasonability of results, which is really important. You can build a model, it can look great, but you need to be very careful and make sure you understand what your model inputs are and what your model limitations are as well. And then we'll get in and kind of discuss some project examples. And I think, we'll have plenty of time, hopefully, at the end of the presentation for any specific questions or follow-ups or anything else we want to cover here. So that's kind of an overview of where we're going today. So the three different types of hydraulic models, dimension-wise, is a one-dimensional, two-dimensional, and three-dimensional hydraulic model. So HEC-RAS now has the capability for 1- and 2-dimensional modeling, which is great because it's a free software. We can work in HEC-RAS and share it with our clients or share it with other engineers. So there's a huge advantage in working in HEC-RAS as opposed to some other softwares that you have to pay for and have licensing for. So now that HEC-RAS has integrated that 2D modeling capabilities, which I think came out in 2015 or a little bit before then, I think it's a huge advantage. So a one-dimensional model we're all familiar with that we learned in our hydraulics class is really kind of like I said in the slide here, a depth averaged unidirectional model that looks at cross-section by cross-section through a riverine system and does a bunch of backwater calculations to assess the hydraulics through that system. You can run both a steady and unsteady model. A lot of the floodplain work that we do and a lot of FEMA's maps are built on 1D modeling. Again, these models have tabular outputs and that is very conducive to mapping purposes and model comparisons, although the 2D modeling capabilities are moving in a direction that make those comparisons a lot easier. So we can run in a 1D model a constant flow rate or a steady state model, as well as a input hydrograph or an unsteady model. But those results are, like I said, depth averaged and unidirectional. So you're really constrained on how you draw your cross sections. For all the seasoned modelers out there, you know, it really, your model results are very dependent on your cross section layout, alignment, etc. And that limitation is not an issue in 2D. And really the biggest advantage of 2D is you can model, you know, lateral flow. You can understand splits and flow paths. If it's a really complex hydraulic situation that you're modeling, rather than, you know, a single thread channel that contains all your flows, a 2D model is really kind of the way to go. And more, you know, I have found that the 2D modeling is actually in a lot of cases easier to build than the 1D model. And it takes a lot of the, I wouldn't say guesswork, but a lot of the user biases potentially of, you know, drawing those cross sections out of the modeling. So the two-dimensional model has its advantages in that it can model those lateral flow situations. It, like the 1D model, though, is depth averaged. So you don't get variation in velocities through the water column. You can see here, this is in that middle picture there. That's the Wines diversion project that we're working on out of Durango, working with Hayes with. And I've got, you know, it's shown in plan view, and you can see the split between the main channel and kind of our fish passage channel there. And then I have a section cut below it. So you can see how, you know, there's variability in flow velocity and direction in plan. And then you also get that variability shown up within that section there. However, you will also notice in that section that those velocities are depth averaged. So that is one of the limitations in a 2D model, is you don't get that vertical variation through the water column. And that's really the largest difference between the two-dimensional and three-dimensional model. Three-dimensional modeling, obviously a lot more data intensive. You need a lot more computational power. You actually build three-dimensional grids and meshes to construct those models, but they are able to provide those variable outputs by depth that you are not able to understand in a two-dimensional model. The applications for a three-dimensional model are really complex hydraulic scenarios where you really have a need to understand that 3D component. Those are really costly models, both to get a license for and to run. So most of our work will be focused between the 1D and 2D models. And I think more and more the industry is moving towards two-dimensional models for almost all applications. So a few applications.
Sorry, I was going to chime in. I mean, the magnitude of order for the Flow 3D, I mean, you're needing $10,000 just for a 6-month lease of the program. That's so you're looking at $20,000 to $40,000 a year when you start to add on the cores. So people are starting to get interested in 3D. Just know.
Yep. In addition to all the time it takes to construct those and run them as well. So applications of a 2D model, you know, we can use them for design. So a lot of times, essentially when I started modeling things in 2D, it was really focused around, my first model was the design of bendway weirs and optimizing the configuration of that. You know, we could vary kind of the underlying terrain and understand the hydraulics under different design configurations. So it's a really useful tool in understanding how various design alternatives or scenarios impact the hydraulics. More recently, we've been working through a few different mudflow projects, which have been really exciting. There are also applications for map revision modeling through FEMA. The latest version of HEC-RAS, and I don't know, Sam, this might have been included in version 5 as well, but you can also do kind of rain on grid hydrologic analyses in HEC-RAS, as well as sediment transport in a 2D environment. So hydraulic design, this one's kind of cool. This is our Tributary T project, and the contractor out there takes drone aerials every so often. So I, in PowerPoint, kind of overlaid our modeling for that with what they're constructing, and you can kind of see in a 100-year event kind of what our modeled flow does through that corridor. You can see the riffles being constructed, the pools, and the sinuosity of the channel. So it's a great tool to kind of understand how your design's functioning, you know, the velocity, shear stresses, and stream power, and make sure you're effectively managing those through design. And I've also shown you all extensively the work we've done at Canyon Creek, and you're all aware of how valuable that was for that project as well. And like I mentioned, with the mudflow, I think it was my last Monday morning meeting for those of you who attended, but there are now options in the latest version of HEC-RAS to model non-Newtonian fluids. So it's become a really useful tool in evaluating mud and debris flows as well. So this is out in Marble, these screenshots on Slate Creek that we're working on, and we're modeling kind of not only the existing mudflow conditions, but our clients interested in building on a parcel out kind of in the debris fan. So we're evaluating a few different mitigation measures as well. And the photo on the right, this is also Slate Creek, and a recent mud flow overtopping the road into Marble and closing it for, I think, several days. So this is a really high risk zone, and it was kind of a neat exercise to model in HEC-RAS. And I'll turn it over to Sam here to go over the other applications.
Yeah, so I'm going to talk a little bit about using a 2D model with for a FEMA application. So that'd be typically either a clomer or a loamer. You can use that to sort of support a 1D model, which I'm going to talk about here in a little bit, in a little bit more detail. But you can see in the image here, you can see in green there's some 1D cross sections. But overlaid all that is a 2D version of this area where in this particular area there's kind of a split flow path where it goes into the developed area, and it was very tricky to model in 1D, so we put it into 2D, got a better sense of where things were going, and then put that back into 1D. One tip though is if you do plan on using 2D, I would discuss it with whatever review agency is going to be in charge of that, just to start the coordinating with them, because although FEMA is moving towards more 2D, it is still pretty new, and some of the regulations particularly are written sort of in a 1D context. So you just got to make sure that you're still complying with the regulations when using 2D. And like Jake mentioned, you can do hydrologic calculations in 2D as well. I think since 2015, you've been able to do rain on grid modeling, but even since then, they've added infiltration and I guess so other soil calculations. So you can do a lot of the stuff that you used to have to kind of go outside to HEC-HMS to do, and you can do those all kind of internally in RAS. I haven't had a chance to play around with that yet, but it's kind of a cool way to combine things. And like Drake mentioned, you can also do sediment transport like in 1D. All right. So we're going to talk a little bit about what data you need to actually put together a 2D model. And before we start, I want to kind of wanted to mention kind of the modeling adage that I learned early in my career, and it's just garbage in, garbage out. And what that means is the data that you use to build your model and the quality of data specifically is going to really influence the level of results you get. If you use really poor resolution terrain data, you're going to get really poor resolution results. If you use a hydrograph that wasn't, wasn't properly analyzed or computed, your results are going to be funky there. So, that's important to keep in mind whenever you're looking at a model, is that your results are limited by what data you put in. All right. So there's kind of three main things you need to make your 2D model. The first is your terrain data. That's going to be, I guess, the underlying ground that the water is going to flow over. The next is some sort of hydrologic data, whether that's an inflow hydrograph or rain on grid, or other hydrologic data that it's basically how the water gets into the model. And then the last thing you're going to need is land cover, which is really your roughness, like your Manning's end value. If we think about our Manning's end equation, that's where that's coming from. You might also need survey data for any bridges or culverts, or soils data if you're doing hydrologic analyses. But really the three main things you need are the terrain, hydrology, and land cover. And specifically, kind of taking the land cover first, you can download a lot of land cover data from the internet, and there's a link in the slide notes too for later. These will be uploaded, and you can apply the different end value to the different land covers listed here on the right side of the screen, and that can kind of make it easy for you. That it can be pretty coarse, and a lot of times you'll want to draw your own land cover to really get the definition that you want. But there are other ways to do that. All right. So let's talk about terrain data, because that's kind of probably the most important piece for your model. So terrain data comes in a raster, and for HEC-RAS specifically, you want a GeoTIFF or a .tif file for your raster. You can get raster information from a lot of different sources. I usually check USGS first, but really, probably the important thing is you want your raster to be a DEM, which is a digital elevation model. And what distinguishes that is that all of the trees and the other vegetation and houses have all been removed from the raster data. These rasters are created from LiDAR data, where essentially you got an airplane flying through the sky, shooting a laser at the ground, and using the time it takes that laser to bounce back to give you an elevation. You pick up a lot of treetops and rooftops and et cetera when you do that. And then there's some post-processing that needs to go in to make it a digital elevation model. All that to say, DEMs, that's kind of what we use as a standard for hydraulic modeling. As far as what resolution you want to use, a raster is, it's essentially a map, and each pixel has an elevation associated with it, and how dense those pixels are represent your resolution. So that the denser those pixels, the better resolution data you have. A lot of times you can find 1 meter resolution data, and I would say that that's a pretty good starting point. But it really depends on what your application is. If you're doing, if you're trying to model like an entire county using rain on grid, maybe 1 meter data is a little too refined, and you don't really need that level of detail. You can go up to 10 meter data, let's say. But if you're doing something that does require a level of detail, then you want to use, I would say, at least 1 meter data. The one kind of neat thing that I do want to mention is you can see on the image here, there's these kind of squares, and those are the 2D cells. Drake's going to talk about those here in a little bit, but those do not necessarily have to be the same size as the cell for your raster. So for example, in this picture here, I believe the terrain data is 1 meter data, but the cell size here is 50 and 10 feet kind of throughout this area. So those don't necessarily have to line up. And then finally, you can modify your terrain data in HEC-RAS to kind of show, pre and post project conditions, and show how things are changing. An example of that, so this is a project along Niagara Creek, which is kind of running along the top here. And for this project, we wanted to look at what would happen if we filled in some of these irrigation ditches that are running south to north here. So, for the pre-project, we just took the unaltered terrain, and for post-project, we filled those in. And this was all done just using HEC-RAS. I didn't have to use any outside software to do that. So it's pretty slick. You can do a lot of stuff with that. All right. So let's talk a little bit about hydrology. I guess by hydrology, I mean, how are you getting water into your model that it's gonna replicate the hydraulics for? Probably the first way, and kind of what's shown on the screen, is a hydrograph. You can get that from like a USGS gauge or maybe a rainfall runoff model. A lot of times, though, in the absence of real data, you can do what's called a quote unquote steady state hydrograph, where instead of having a nice bell curve, you kind of ramp up to your starting point and then put in a constant discharge. And that's sort of a way you can replicate a steady state 1D model in 2D. A steady state model uses a constant discharge; it doesn't vary with time. 2D models are inherently unsteady, but if you put in a constant discharge in there, it's essentially replicating, a steady state condition. One note with that, though, is that you do need to have a ramp up period. So let's say, your peak discharge is, 10,000 CFS. You don't want to immediately start your simulation putting in 10,000 CFS. If you were to do that, as the cells are wetted, it will produce a lot of errors. So instead, what you do is you'll start at, maybe 100 CFS, and then over time you sort of ramp up all the way to whatever your peak is.
Hey, Sam, can we ask questions along the way?
Yeah, please do.
Would you want to make an informed decision on what you'd start with for your ramp up period? Like, whatever the low flow is, or like average base flow or something, or would you just start with something really minimal?
I would even ramp up to something like the base flow or the normal flow. So, let's say your base flow was like 100 CFS. I'd start at, 10, and maybe over the course of 30 minutes of simulated time, ramp that up to 100, and then, ramp it up from there if you're modeling flood flows. Just to make sure you're not getting any errors from the startup or initial conditions. Did that help?
Yeah, thanks.
Perfect. And the last thing I'll mention is that you can also do precipitation modeling here too. So instead of having flow come from one location where you're applying your hydrograph, you can kind of apply it all over the model and model the rain as it produces runoff and flows out of the model. You do probably want to use an infiltration layer when you do that, so you can account for water seeping into the soil. Or alternatively, you can model that in a separate rainfall runoff model. That's at my last job, we did a lot of that, where we would model the excess precipitation, but we'd have to use an HMS model to sort of capture that initial infiltration. All right, and I'm going to hand this over to Drake.
All right. Well, so the 2D model functions very similar to the 1D model as far as your needing support file structure. So ultimately, similar with the 1D model, you have a geometry file, you have a flow file, and those are really brought together in a plan file, which is ultimately used to run the model. So in this segment, I'll kind of go over the components to each of those supporting files and considerations for putting each of those together. So I think we'll start with the geometry file. Sam had kind of gone over this just now, but the data you need for your geometry file is your terrain data and your land use data. And so you want to associate or bring in that geotiff into your model and then upload that into your geometry model for which you're doing that 2D analysis. So that's one layer. The next layer, if you go to the next slide, Sam, is your land use model. And two notes I'll make about these two pieces of information. Sam had shown an awesome example of what you can do in HEC-RAS as far as terrain modifications and grading. There are a lot of new, really useful tools, but you can also export design surfaces, surveyed surfaces, etc., from AutoCAD. And to do that, you export from AutoCAD as a GeoTIFF, and you import that TIFF into HEC-RAS. It creates kind of a unique file to HEC-RAS called an HDF, and that's really what HEC-RAS uses to analyze that vertical component of the underlying terrain. Sam had also mentioned, the National Land Use Cover data set, NLCD, is a great starting point, especially if you have, a larger scope model. Say it covers, a large watershed within the county. That can be a great starting point for your land cover or your roughness data. But usually, a lot of the models I create are focused on design, in which case, we need to delineate something a little bit more specific to the project. And so typically I have to go through kind of the process of creating a what's essentially a polygon shape file of the different land use coverages or different roughness areas within my modeled area. So it's important to get your terrain and the extents of that terrain such that it covers your entire, desired modeled area, as well as a roughness layer that'll essentially lay upon that to start composing your geometry. So once you associate both those data layers in your geometry, you can then start putting together a 2D flow area. This 2D flow area is sort of the extents of your model. And you can digitize this in both kind of the geometry editor, and now HEC-RAS has kind of made a lot of the editing features really easy in what's called the RAS mapper. So you can make a lot of these geometry edits in either, but for the sake of this presentation, I'll kind of focus on the geometry editor up here. So to do that, you create this 2D flow area. That's that red circle button highlighted there on the slide. And you essentially sort of digitize or outline the extents of your model. And I usually like to be pretty thoughtful when creating a model, especially at a first cut, to make sure I have enough extents as I anticipate needing, more than what might be the floodplain. But I also don't want to go too crazy with the area that I delineate here, because this 2D flow area translates into individual cells that are used in the computation, and too many cells can really bog down the runtime. So you can really extend the runtime of your model if you have too large of a 2D flow area. So you want to make an informed guess as to what those extents might be, and you can always come back and change it later. I usually have to go through a few model runs to sort of tailor my input parameters to a specific project, and the extents of this 2D flow area being one of them. So that's the first step. After you get your terrain and your land use cover together, you need to digitize that 2D flow area. And once that polygon is drawn, you then create the 2D mesh, which is a series of grid cells that essentially sample the underlying terrain and roughness data. So with this mesh, you can specify the cell size. Like Sam mentioned, the cell size of your 2D mesh does not need to be equivalent to the raster resolution of your input terrain data or the raster resolution of your land cover data. I usually, depending on kind of the scope of the project or the detail of the model, I usually start at a spacing of around 10 feet. And something as detailed as that Canyon Creek example, I was looking at 1 foot or less as a starting point. So the more detailed you get with these models, the more refined you want that spacing to be. But keep in mind, the more cells mean more computation time. And ultimately, you want to work through the model in a way that makes your computation time, most efficient. So you don't want to add extraneous data that will bog down your machine and runtime. So once you create that spacing, you hit compute, and it'll create what is shown on the screen here, which is essentially, a very regular kind of looking 2D mesh that is shown on equal intervals and covers your entire 2D flow area that you digitized at the spacing you specified. And so I've drawn up this schematic here because this is one of the most critical kind of intuitions that you need as a 2D modeler to understand is how this 2D mesh really functions. So this image on the left here is straight out of the HEC-RAS manual, and it shows how flow is distributed between mesh cells. So, this large blue arrow demonstrates, flow coming into one cell. It can really leave that cell in 8 different directions for a regular cell. So it can leave to the cell to the north, the northeast, the east, etc. The 8 adjacent cells flow can be transferred to and from. And the way it does this is I like to sort of think about it as a series of kind of cross sections that are sampled along the edges of those cell faces. So I've kind of drawn up a 3D kind of ortho view of one of these mesh cells to help give you kind of a better understanding of what's really functioning behind that 2D mesh. So you can see up top, you've got that regular kind of looking mesh cell, but it's sampling that underlying terrain. So the only data that the model has is really what is sampled at each of those mesh cell edges. So you need to make sure in your mesh development that those edges reflect kind of the critical points in the terrain to make sure that you capture everything that would influence the hydraulics appropriately. So if we go to the next slide, the way you do that is through 2D break lines. So you digitize these 2D break lines, and typically I like to draw the break lines so that I capture the high points. It's really critical to capture a high bank or some other obstruction in the flow path, and make sure your cell face is aligned with that high point so the model actually can see that high point. Just because it shows up in your terrain doesn't necessarily mean it will be modeled unless your 2D mesh reflects, kind of those critical areas in the terrain. So once you kind of draw break lines around those critical areas, what you can do is you can enforce those break lines into that 2D mesh cell, and it'll essentially force that cell boundary to align with that line that you've drawn. So once you've kind of created a 2D mesh and enforced break lines to capture critical elements within the terrain data, you also need to input boundary condition lines. And so this is kind of going back to Sam's slide about input hydrology. You need to specify where on the terrain that flow is coming into and where it's exiting that 2D mesh area. So typically, you'll have a boundary condition line at the upstream extents of your model, or multiple upstream extents of your model if you have multiple flow paths flowing into your model. You can also, a new feature in HEC-RAS is have internal boundary condition lines. So you can draw a boundary condition line to add flow into your model in an area that's internal to that 2D mesh. And then you also need to digitize a boundary condition line for your outflow. So how that flow exits your 2D mesh, and where in that 2D mesh flow can exit. So that's another critical element. So you need to digitize, where flow enters and where flow exits that 2D mesh. Similarly, a new feature in HEC-RAS is internal crossings in a 2D model, which is really nice. So here's kind of an example, and this modeling these can be a little finicky, and there's a lot of details that needs to kind of go into this, but it's very similar to 1D. Once you kind of modeled an internal boundary condition, you can associate a structure with that, and with the structure you can input all the data associated with a roadway or a culvert, very similar to what you have done in HEC-RAS 1D. So that's very similar, and that's something that you can do in 2D, is include structures into that 2D mesh. So those are kind of the key elements of the geometry data. As I mentioned earlier in the presentation, the 2D model only allows unsteady inputs. And as Sam alluded to, you kind of want to run up period to that input, whether it is a hydrograph input or kind of a quasi steady state hydrologic input there. So the way you do this is you open that unsteady flow tab, very similar to what you would do in 1D, and then in that screen that pops up, you'll see all the boundary condition lines that you had drawn in your geometry data show up. And so you can either input a flow hydrograph or a rating curve, or have a normal depth for flow to exit that 2D mesh area. So you essentially click on one of these boundary condition lines. You can specify what kind of condition it is to define your inflow hydrology. You click on flow hydrograph. And I think if you go to the next slide, this is where you can either input, as Sam was saying, kind of a hydrograph from a rainfall runoff model, or if you only have, peak flow rates, like we do a lot of times in floodplain modeling, you can enter in quasi steady state hydrograph, where you just, run the model at that peak flow rate for a sufficient amount of time so that it reaches equilibrium in the model. So the amount of flow into your model equals the amount of flow out. So it's a time series data that you would enter into those locations, shown here as a graph, obviously. And then the outflow, it's very similar to HEC-RAS. You need kind of the slope of that outflow location for a normal depth analysis, and that'll allow flow to leave that 2D mesh area. If there's a rating curve or some other way you want to define your downstream limit, you can also do that depending on what that associated feature is. Yep, and that's where you enter in the slope there. So again, I'm staying pretty high level with this, but another thing that you can add in the flow data now is the non-Newtonian parameters that I discussed briefly during my last Friday morning brown bag. So in options, you have the ability to modify kind of your volumetric concentration of sediment in the flow, incoming flow hydrograph, as well as some of those non-Newtonian parameters. So if you're interested in doing a mud or debris flow analysis, that is where you make those adjustments. And so similar to 1D, you bring all this data together in a plan file. So the plan you open up very similar to the 1D button in the model. You specified the associated geometry file that you've created in the flow file. And then you've got the option to run a few different programs. I always select kind of these three: the geometry preprocessor, the unsteady flow simulation. Obviously, click the sediment if you're doing a 2D sediment model, and then your post processor. Those are pretty standard. One of the things that I will focus everyone's attention on is the computational interval. And I think Sam will dig into this a little bit more when he talks about kind of the reasonableness of results and other considerations. But depending on your cell size for your 2D mesh, kind of the underlying terrain, the velocity of flow, the required computational interval, or the time in which a new computation is run to distribute flow between each cell, is really dependent on kind of those parameters, the velocity and the cell size. And you want to make sure that that's fine-tuned enough where you don't get model instabilities. In other words, you want to make sure that you capture at each time computational interval the hydraulics through the system. So usually I like starting it out around probably 1 second is a good place to start. Obviously, it could be more or less depending on your cell size and your underlying terrain. And then your mapping output interval is another one. So in RAS Mapper, you can kind of specify at what interval in the simulation do you want it to create a new map that you can look at. And, if you're looking at how a hydrograph flows through a system, you might want this to output every 1 minute or so you can watch how that water moves through your model there. But obviously, if it's a quasi-steady state model, it doesn't need to be that fine-tuned. So you can do something similar to the other outputs at 15-minute interval or whatever is commensurate with your runtime. Another important thing to focus on in the plan data is your computation options and tolerances. So in this menu, you can modify, if you go to the next slide, the equation set for your 2D model. This is a big one to be aware of. Either you can run kind of a full energy equation for your 2D model, or you can run full momentum. I think HEC-RAS now has a few different engines to run the full momentum equation set. I've found that in almost every model I've built, the momentum equation, though it takes longer to run, does give you much better results. If you're doing kind of a high level evaluation that we've been talking about, kind of a watershed level analysis, I think you're probably all right with that diffusion wave or energy equation set. But if you're doing any sort of design work, I would certainly recommend using the full momentum equation set for your computations there. And that's edited through that options and tolerances in your plan. There are a few other options in there. None of them are terribly pertinent to getting you going, at least at the onset of a project. You are able to kind of ramp up or do that first into the hydrograph kind of prior to mapping your results. And there are a few options for ramping up, a few other, smaller options too. That are really refined to kind of case by case need there. But The momentum one is the one that I wanted to bring everyone's attention to there. And then once you have all that data together, you can go ahead and compute your model. And then, yeah, you should have a solid 2D model run. And usually HEC-RAS is pretty good with their errors now and being descriptive. And if you do run into any errors, it'll at least give you some information on what those errors are and how might you go about fixing those. So those are kind of the real high level basics to building a 2D model, the needed information and model components there.
Yeah, just sort of piggybacking on some of the errors. Sometimes when you build a model, it can be helpful to run it at a larger computation interval for the first time, just to sort of weed out any of those errors and see what's going on. These model runs do tend to take a lot longer than a 1D model run. 1D would run in, a couple seconds usually. A 2D model run could take several hours or days. And so if running it at a larger time step lets you get through the simulation a little bit faster and sort of weed out any errors before maybe you do a final run at a more refined time step. All right, I'm going to try and go quickly here and talk a little bit about viewing the results. So this is the RAS mapper. This is where you will see the model results after the model is run. Over here on the left, you've got a couple things. You've got the geometries. Like Drake was saying, everything that we talked about here will also show up in RAS mapper. And then you've got your results. And each of these items here represents a different model run. So for each of these model runs, you can open it up and you can add different layers in here. So you can look at your depth, you can look at your velocity, you can look at your water surface elevation. You can add a whole host of other ones. You can add shear stress, you can add Carnot number, all sorts of information. So really anything that you would want to look at hydraulically, you can find as a map in here. The neat thing is throughout the course of the simulation, you can kind of scroll through each computation, or rather each mapping interval that you set, and see what's going on at each of those time steps. You can also have your trains in here. As you can see, there's a lot of trains in this model. You can turn those off and on. This is also where you will associate with them, or associate the trains with the different models. And then I guess I got two things to mention before we move on from this. There's this profile lines option up here. This is where you can draw a line in your model and extract a hydrograph or see kind of in a cross-section view what the water surface elevation or depth or velocity or whatever you're interested in is doing at a particular location. So like in this instance, this is a low head dam kind of right across here. You might draw a profile line across the face of this dam and then look at that profile line and see what your hydrograph looks like, what your water surface elevation looks like at different intervals. And the last thing I'll mention is you kind of see these white lines here. Those are velocity tracers, and those are up here. That can kind of help visually show you where the flow is going. So here you can see the flow is kind of routing around here, or go through here. I just think they're kind of neat, and they tend to impress clients. So I just wanted to point those out. All right, so let's talk about how we know whether our results are reasonable. If we go back for a second, this can look really pretty, but how do we know that this is actually, reflective of the real world and not just, something we created on a computer? There's a couple different ways to look at that. The first is under your unsteady flow analysis, there's your computation log file and your runtime messages. Your computation log file is going to list an error percentage in there, and it's essentially doing a volume accounting. It's looking at, is the flow going in equal to the flow going out? And if that percentage is too high, usually I think anything over 1% is probably means that it's not doing a good job. But that just means that as HEC-RAS is running its calculations, it's not balancing the flow, and so it's introducing a little bit of error into there. So if your computation, if your percent error is over 1%, I would go back to your model, change your time step, get in there and try to fix some things. The other thing that it will give you is the runtime errors. So as the model is running, if it can't balance the hydraulic equations, it will note the time step and some of the information about when that error occurred. It'll list like the cell and the magnitude of the error and the water surface elevation difference. And so you can throw some of that information into Excel and get an idea of, oh, okay, at these 3 cells, we're seeing a lot of errors. Let's go in and revise those a little bit to make those work. Another way to check for the reasonableness is your Courant number. And that's really important for 2D modeling. So this is the Courant equation here. So your Cn is equal to your velocity times time over depth. And essentially what that's saying is if your water is moving fast enough that at each individual cell, it's moving through a cell before it can do a computation, it's going to give you a very high Courant number. So essentially what you want is your cell spacing and your velocity to be balanced such, and your cell spacing kind of be represented by D here. You want those to be balanced such that as water is moving through the simulation at each time step, it's interacting with each of those cells. And so if you get that, that means that your Courant is less than 1, and that's usually where you want to be. Let's see, another thing to look at is your velocity. If we go back just for a second here, so the velocity is the map that's shown on the background here. You can see in areas where water is moving a little bit faster, it's redder. A lot of times, if there are errors in the model, that velocity will get very, very high. That can be indicative of an error. Usually it means that there's something wrong with the cells or the break lines, and for the equations to balance, water has to start going at 50 feet per second, 100 feet per second, something that's just unreasonable. So turning on your velocity layer and then turning on the maximum volume, or sorry, the maximum velocity can kind of help identify some of those areas.
Tim, if that Courant number is high, would you want to increase the cell size so that water spends longer in each cell? Or decrease it?
I would actually decrease your time step.
Okay.
So in this equation, your D, that's your cell size. Your T, that's your computational time step. So to get that less than 1, there's 2 things you can do. You can make that bigger. You make your cell size bigger, or you can decrease your time step, and that's probably where I'd start. There is also an option in the plan data to have the model automatically adjust your time step as the model runs based on your Courant number. So at each time step, it's calculating the Courant number, and if it sees anywhere where you're above 1, it will decrease your time step to keep that less than 1. So that's a handy feature in there. Okay, so the last thing to check is your outflow. A lot of times you'll have an inflow hydrograph, and whether that's coming from a rainfall runoff model or coming from a peak flow quasi-steady model, you want to make sure that all of the flooding or all of the flow in your model is making it all the way to the downstream end of your model. So you can check your outflow and make sure that it either matches your peak inflow for a steady state model, or that you're on the falling limb of your hydrograph. If you don't see that, if you haven't reached your peak yet at your outflow, or you're not at the falling limb, that means that your simulation wasn't run for long enough, and you need to run your simulation for longer to let the water flow all the way through the model to the outflow. All right, we got about 5 minutes left, and we're going to spend just a little bit of time just showing a couple of examples. So I'm going to stop presenting for a second and share my other screen here. All right. So this model here, this is the Lowhead VAM I was showing you earlier. This is in Sioux Falls. So one kind of cool thing that we use some 2D modeling for is we looked at the existing conditions Lowhead Dam. See if I can turn on the cell mesh here. Turn off that guy. And basically I use those profile lines along the face of this dam to determine where water flowed on this dam at different discharges. So whether that is, let me go. I just want to show that. Anyway, so whether it was at low flow or during, the 500-year event, where water was going. And we use that to make a chart that said, okay, and at different sections of the dam, this is how much flow is going over each individual section. And then we use that to inform our design. So we said, oh, on the left side of the dam, that really doesn't start to show up until you get to, 7,000 CFS or so. Let's design our the elevation of our weirs over the dam to reflect that. And that's just not something you can really do in 1D. So I thought that was kind of a cool application. I'm going to hand it off to Drake now to, I think he's got a couple examples as well.
Sure, yeah. So one unique application is, we're working on this project in Colorado Springs, and we're trying to understand, with development upstream, what kind of impacts that has to the existing river corridor out there. So we developed kind of a preliminary hydraulic model to, this is a map of the hydraulics to understand the velocity through the system. And we've also kind of done a preliminary model of the future hydrology through there to identify any high velocity areas. And we were able to export that results map as a raster and upload it into a tablet for a site visit. And we went out there with the client, and here is kind of that proposed conditions model. And we were able to kind of walk this reach and identify areas where we were seeing higher velocities, where there could be opportunities to reduce those. We could overlay those with the existing wetlands and what we were observing on site. So I thought that was a really unique application. It was also good to show the client our capabilities of mapping these detailed hydraulics and how they can inform our design process. And it's also nice to be able to take that with you out into the field. Another thing I wanted to share, Brianna has also been doing a great job with 2D modeling and debris flow analyses. And this is kind of some of the maps that she's developed for one of our projects outside of Aspen. So they've kind of provided some existing survey and conceptual locations for a future structure. And we're able to kind of model not only clear water flow and provide them depths and elevations relative to that proposed residence location, but we can also do the same for mud flows. So I thought that's kind of a unique application, and we're doing that at multiple locations right now. So another example showing how you can export the results and really communicate something very, very useful to your clients here with 2D modeling. I believe if we go back to our final slide is really kind of focused around resources. So in addition to kind of the user's manual that HEC-RAS has that goes into the specifics with 2D modeling, I think there's a separate even 2D modeling manual that's a really good reference. There are a lot of kind of online references as well. The RAS solution blog has been one of my go-tos if I run into an issue or am having trouble figuring out a certain model component. That's a nice reference, and there are a lot more on YouTube. You just need to be careful what videos or what references you watch and make sure they're from a reputable source, obviously. And if you have any other questions, of course, you can ask myself or Sam or Brianna. Even in this office is becoming pretty good at 2D modeling too. So we're all available in here as resources. I know this presentation was very high level, but we made an attempt to kind of cover all of the basics here. And I'd be certainly happy to go over anything in more detail if you all wish. So I guess we don't have much time, but we could open it up to questions now if anyone has anything specific that they want to ask.
Hey Drake, this is Hayes here. I had a quick question on your cell slide where you had the flow going to the different locations.
Mm-hmm.
So does the does the terrain that gets brought into that cell, is it just the 4 points of the square, so to speak, that route that flow in the other directions, or does it actually take into consideration the terrain in between those points?
It takes into consideration the terrain in between.
Oh wow. Okay. Interesting.
Yeah.
So
go ahead,
yeah,
Jake. You take
that's
it.
what I was trying to get at with my schematic in that 3D section there where I've drawn that underlying terrain.
Yeah, no, and that's what I thought you were saying, but I just wanted to double check. I'd always thought that it was just based on the 4 points, and then a center point. Maybe that was the older 2D modeling, was how they were doing that. But it's good to know that they have incorporated that.
Any other questions?
One of my biggest hindrances and being able to perform hydraulic modeling capably is my inexperience managing surfaces and having to go back and forth between CAD and HEC-RAS. And do you feel like these new improvements, or maybe they're not even new, but that 2D HEC-RAS programs are much more streamlined than what we used to have to do with 1D, where you are going back and forth a lot? Like, do these digest surfaces, or do you do a lot of pre-processing before using, for example, a LiDAR surface to build your mesh from? Your terrain from?
I mean, you still have to do some pre-processing to go from the raw LiDAR data to a DEM.
Mm-hmm.
I guess I would say, once you get it into RAS, you very rarely have to go back and forth.
Nice.
Like I was mentioning before, that there's a lot of editing tools in RAS that you can use to modify the mesh if you want to look at proposed conditions, or like Drake said, you can also do stuff with Civil 3D. I will say that it can be helpful to keep the file structure, keep that clean. That can be an issue sometimes too. You just want to make sure that if you have a model, you're saving all of your surfaces inside the model folder, just so things stay associated. But all that to say, I do think it is a bit cleaner than it was in the past.
Cool. Thank you.
Yeah, Natalie, I mean, when we had Pfeiffer doing it, he never even got into CAD ever. And so even doing the 1D and the beta stuff out there for drawing cross sections, importing shape files, you never actually have to touch CAD anymore. And so we found out, and it's actually a lot easier to paste some LiDAR surfaces in HEC-RAS, just like you would do in CAD, layer them on top kind of thing, than it actually is to play with CAD. So if you can just keep them all in GIS or just in HEC-RAS, just don't touch CAD unless you have to.
Awesome. Thanks.
Hey, great presentation, you guys. Ian here. One question as far as the submittals to FEMA for loamers and clomers. Are they, does Mile High Flood District accept 2D models for loamers and clomers now, or does FEMA accept them? I'm curious about that.
We are working with Mile High now. We're doing a 2D model that we're using to inform a 1D model. So I guess I would say I would talk with them before using just a 2D model to map your floodplain. I know FEMA, the broader FEMA will do 2D models, but again, I would, I guess check with the region and make sure, they're comfortable with it. Just because, specifically with the floodway, the way the floodway regulations are written, that it sort of assumes a 1D environment. And there are ways to model a floodway in 2D, but I guess it's a little more complicated. So I would just talk with them first if there's something you need to do.
Last I heard, there was a moratorium in the city and county of Denver for doing anything via 2D. I've actually reached out to FEMA a couple times about this and seeing if they're going to start to put some guidance together. I think this is one issue where the technology got ahead of the regulations. And the biggest issue is then when you start to when you start to like evaluate a cross section, in a 2D model, you're going to get super elevated flow. So to your point, we've used 2D to inform split flow channel alignment of cross sections, and it's been very beneficial with regards to that. But when you start getting into 2D, it's a little bit of a whole nother world. But we all know County of Boulder has utilized Mike Flood 2D over there for maybe 10 years or so now. Maybe Sam, you maybe know this. Maybe it's been since just the floods, but it's been a while. I'd be cautious going towards 2D for regulatory reasons at this time.
Yeah. One thing I will add is 2D now has a feature where you can analyze rasters against one another, so it's a lot easier to compare two results maps and understand if there's a rise or not across that entire distributed area in this latest version than there was previously. So even the modeling itself now has the capabilities for those comparisons where you don't even have to really rely on those sections as much.
Yeah, that kind of goes back to Natalie's point where you don't have to export stuff to CAD or GIS anymore. If you've got a pre-project and post-project condition, you can look at the velocities and compare those Wright and RAS and see where the changes are happening.
I'd be curious to know your all's thoughts on completing and certifying a no-rise via 2D. Possible, feasible?
Yeah, I think that would be tricky, just because
it's a loaded question, and
yeah,
that's sort of what I was getting at. It's going to be damn near impossible ever to do a no-rise certification via 2D hydraulic modeling evaluation. Period. It's just every little intricate modification of the cells as you overlap existing and proposed grading will never show no. It's going to be impossible.
Mm-hmm. Yeah, and just to explain for those who maybe aren't aware, no rise, you essentially want to show that after you complete your project, the water surface elevations didn't increase anywhere. And in a 1D model, you just have to show that at every place you've drawn your cross sections, which, maybe let's say you got 50 something cross sections. But with a 2D, you've got 100,000 cells, and at any one of those cells, you might see an increase at some time period during your simulation. Which would, sort of violate the no rise.